All right, welcome to Unit 4, Probability, Random Variables, and Probability Distributions. In this video, we're going to focus on random variables and probability distributions. This is kind of an intro video just to give you an idea of what random variables are. So let's dive right in. First off, what is a random variable? A random variable takes numerical values that describe the outcomes of some chance process. So in fact, it's actually very, very similar to algebra class, right? What is a variable in algebra? It is a letter that we use in place of a number that we do not know. Well, that is the exact same thing a random variable is in statistics. It's a letter that we use in place of an outcome that we do not know. So that's why we add the word random in front of it, because that outcome comes from a random process. So a random variable is a variable like X. We usually use capital letters to represent random variables. So it's a variable that represents an outcome to a random chance process. Now, the key thing here is that random variables can only take on numerical values. So if the outcome of the chance process is a word like red or green, then that's not going to be an official random variable because random variables focus on numerical outcomes only. Now, let's talk about the two different types of random variables that we are going to explore in this unit. First, we have a discrete random variable. A discrete random variable is a random variable that can take on a countable or listable set of outcomes. So if you could make a finite list of all the individual outcomes that can happen, it's going to be a discrete random variable. The other characteristic of a discrete random variable is that each outcome has a probability associated with it. So every single outcome has an exact probability of that outcome of occurring mentioned with it. And all of those probabilities have to add up to 1. A very, very simple example of this would be if I let D be the random variable for the value that you get when you roll a die. So if I roll a die, I could list all the outcomes, 1, 2, 3, 4, 5, 6. That makes it a countable or a listable set of outcomes. And every single one of those outcomes has a probability associated with it, and they all happen to be 1/6. All right, a continuous random variable is a random variable that can take on an unlistable amount of outcomes across some interval. So here, the possible outcomes is way too long of a list. It's basically an infinite list over an interval where I just cannot possibly list all the different outcomes that could happen. There are so many infinite outcomes that we can't even find a probability to attach to each outcome. I mean, if we can't make a list of all the outcomes, how can we possibly make a list of all the probabilities? A very simple example of this would be if I let S be the random variable for the amount of seconds that Jimmy takes a shower. Now, maybe Jimmy knows that he takes a shower in an interval anywhere from 0 to 2,000 seconds. But within that interval, 0 to 2,000 seconds, there's an unlistable amount of outcomes. Now, you can't just think about whole numbers here because, if you got a stopwatch, maybe you got 2 decimals. So a shower could take 99.24 seconds or a shower could take 526.37 seconds. And when you start to think about decimals, then you really do realize how that interval from 0 to 2,000 seconds is infinite. And that's what makes that a continuous random variable. So these are the two different types of random variables that we have. Now, what do you do next once you understand a random variable? Well, then you kind of want to make a picture of it, right? And this is what we call a probability distribution. A probability distribution is any representation of the possible outcomes of that random variable and their associated probabilities. So for a probability distribution to be, exact, what you have to have is all of the outcomes listed and all of the probabilities listed with it. So it could be in the form of a table, a graph, or even a function. Now, the best part about this is once you have this table, once you have this graph, once you have this function, which, again, if you kind of think about it, it's a lot like algebra, right? Like in algebra, you could understand a function through looking at the function, looking at its graph, or looking at a table of values. So it's kind of very similar to that. But regardless, once you have this picture in front of you, once you have this representation of all of your outcomes and their probabilities, you could talk about the shape, the center, and the spread of that distribution. So the shape, we know about skewed left, skewed right, uniform, symmetric. For the center, we talk about median, which I'll mention in one moment. And then spread is, are there a ton of outcomes? Are they spread way out? Or are there a very small amount of outcomes that are not spread at all? So I did say I was going to talk about median. Now remember, median is actually pretty easy to find. The definition of the median is that there's 50% above it, 50% below it. So with a probability distribution, the median is the value that has at least 50% above it and at least 50% below it. So you got to be able to find that median and say, hey, there's 50% of data at or above, and there's 50% of data at or below. All right. So let's take a look at our very first example here. Here is an example of a probability distribution. Let's look at the random variable Q. Now, Q represents the number of employees who work at a certain restaurant on a given day. So the following table shows the probability distribution of the random variable Q. So on the left-hand side of this table, we see the possible outcomes, 20, 21, 22, 23, 24, and we see the probabilities associated with each outcome. For example, what's the probability that there are 22 employees working tomorrow? Well, 10%. So the first question I have for you is this discrete or continuous? Well, the fact that I'm looking at a list of all the outcomes and all the probabilities, that is literally the definition of it being discrete. Remember, discrete, the outcomes are listable, and every outcome has a probability associated with it. Now, another reason why this is not continuous is decimals are not allowed. Like, on Tuesday night, you cannot have 21.6 employees working. That doesn't even make sense. You can have 20, you can have 21, you can have 22, you can't have 21.6. All right, what is the shape of the distribution? Well, for that, you kind of just have to think about it, or you could kind of draw yourself your own little picture here. So if I think about a number line, and remember, number line's got to go smallest to largest. So if I think about each of these outcomes here, and think about the probabilities, right? 20 is at 10%, 21 is at 10%, 22 is at 10%, and then 23 jumps way up to 40%, and then 24 is at 30%. So if I think about it like looking at a picture like that, I see that it's skewed to the left, right? Where there are far fewer likelihood that there are 20, 21, 22 people working, there's much more likely it's 23 or 24. All right, so it's skewed to the left. What is the center? So if we think about the median here, right, where's the 50th percentile, right? What value is 50% above it or below it? So if we look at 23, right, 23 has 40, 50, 60, 70% at or below, and it also has 70% at or above. No other value has 50% at and below it and 50% at or above it. If I look at 22, for example, well, there's 30% below, and then there's 80% above. Well, we need 50% on each side. So the only number that has that would be 23, so 23 would be considered the median. What is the probability that there are at least 22 employees on any given day? So we're trying to find the probability that Q is greater than or equal to 22. So at least 22 means 22 or more. So here we're just going to add up the values that are 22 or more. So that's going to be 80% or 0.80. So that's pretty easy to find. All right, let's look at a second example here. At a school fundraising event, there's a raffle. Let P be the random variable for how much you could win in the raffle. So once again, I have a table. Now the only difference here is this table goes horizontally rather than vertical. Well, it doesn't matter at all. So we have all the different outcomes. It's random. I don't know how much money I'm going to win. I could win 1, 5, 10, 20, or $50. And the probabilities are under each. So is this discrete or continuous? Well, again, the fact that I'm looking at a list of all the outcomes with their probabilities instantly tells me that this is a discrete random variable. And always make sure that the probabilities add up to 1 or else something is way wrong. All right, what is the shape of this? Well, this one's going to be skewed to the right. If I think about it, the lower numbers on the left are much more likely. 1 is really high, 5 is fairly high, and then 10 really drops off, 20 and 50 really, really drop off. So that's going to be skewed to the right. What's the center? Well, again, I'm looking for that number with 50% above and below it. And the only number that actually meets that is going to be $1. So even though $1 is not anywhere what somebody would consider the center because it's way to the left, it is the only value that has 50% at or above it and 50% at or below it. Some people will jump and try to say 5 maybe, but 5 has 40% at or below it. I'm sorry, I said that the wrong way. 5 has 40% at or above it. Well, that's not going to get you the median, right? We need the value that has 50% at or above, 50% at or below. And the only number that has that is 1. All right, what is the probability you win at least $5? So I'm trying to find the probability that P is greater than or equal to $5. And, well, let's see here. So greater than or equal to is going to be 5 or anything above. And that is going to be adding all those together, which you get 40%. or 0.40. Now, the other way that you could have gotten that answer is to think about the one outcome that you do not want. If I'm looking for 5 or more, the only outcome I don't want is $1. So if I do 1 minus 0.6, I also arrive at the 0.4. All right, another example here. Now, this time we see a graph. Let S represent the age of the attendees at a local concert. The following histogram shows the probability distribution of the random variable. So we got the ages across the bottom, 32 through to 40, and then we have the probabilities. This time, instead of me writing down the probabilities for you, I'm expressing the probabilities as the height of each bar. So we have to do a little bit of estimating in terms of what the probability of each is. But this is certainly discrete. Why? Well, once again, I have a list in front of me of all the different ages. Cannot be more, cannot be less, and there's no decimals here. Each each outcome, for example, 33, has a probability associated with it, looks to be around 3%. The outcome of 37 years old looks to be around maybe 14%. But each outcome has its probability associated with it. That's an instant sign of a discrete random variable. What is the shape? Well, once again, pretty easy to see that the shape is skewed to the left, where the outcomes on the lower end are less likely than the outcomes on the right end. What's the center? Well, again, we're looking for that 50% on each side. And I'm going to go ahead and say probably right around 38 has 50% at or above, 50% at or below. 37 is going to be close, but I don't think they're all going to add up to 57 or to 50% at or below 37. All right, what is the probability that a randomly selected attendee is 37 or 40? So we're trying to find the probability that S equals 37 or 40. Now, if you remember OR probability, all we got to do is find the probability of 37, which is about 14%, 0.14. The probability of 40 looks to be about 7%. Again, it's hard to tell with these heights, but, even if somebody said 8% or even 9% for 40, I think I'd give that full credit. But again, we have to add these together. Now, you may be asking, well, wait a minute. The OR formula, you should be subtracting the AND. Well, that's impossible. These are mutually exclusive. Nobody could be 37 and 40 at the same time. You're 37 or you're 40. You cannot be both, so I don't have to worry about subtracting anything. So add those two probabilities together, and you get 0.21 for 37 or 40. All right, now here's our first example of a continuous random variable. Let's let T be the amount of time it takes Josh to get to work each day in minutes. Now, a couple of things that make this continuous. A, there's a curve. I see this curve. Now, the other reason that makes this continuous is that I have intervals across the bottom. For example, from 2 to 3, right? There are lots of times between 2 and 3. Now, there's 2.1 minutes, there's 2.2 minutes, there's 2.5 minutes, but I can even go further. If you got a stopwatch, you could even be 2.56 minutes, 2.57 minutes. So even if I just look from 2 to 3 minutes, there's technically an infinite number of outcomes. And there's no way that you could locate each outcome and find its associated probability. I mean, you could estimate the probability of 3 by going up and over, but again, you cannot find the probability of each and every single outcome here because there are so many of them, especially when you consider the fact that you got decimals when you're talking about the number of minutes it takes Josh to get to work. So this is definitely an example of a continuous. Now, what is the shape of the distribution? Come on, skewed to the right. The outcomes on the left, well, I could say it that way. The outcomes on the left are far more likely than the outcomes on the right. That's going to be skewed to the right. Now, this next question is a little bit of a trick one. What is the probability that the amount of time it takes Josh to get to work is more than 6 minutes? Well, this is actually impossible to figure out. I could shade this in. I could put a line here at 6, and I could shade in anything above 6, but I can't actually find that probability because there are so many outcomes above 6, right? You might look like there's a very little probability, but there's tons of outcomes, right? I got 6.1, 6.2, 6.3 minutes, 6.34 minutes, 6.35 minutes. I can't find each and every one of those probabilities and add them together. So I will say that when you are a continuous random variable, it's very difficult to get probabilities. But next unit, so we got a little bit of time, but next unit we will start to explore possible ways that you can actually answer probability questions. But I'm not going to lie to you, it is still a little bit tricky, but we will eventually get to how to do it. All right, now the only way that I've yet to show you to represent a probability distribution is with a function. That's because it's really weird. Let me try to explain this as best I can. The only other way that a probability distribution can be represented is a function. Now, this can only be done in special situations that we are going to discuss at the end of this unit. But for right now, let's just think about and try to understand this. Let's let M be the random variable for how many free throws J can make out of 8 shots. Now this is continuous because if he has 8 shots and I want to list how many different ways he could make, or if I want to list how many different makes he could have, I could easily make that list. So the random variable M could be 0 shots, 1 shot, 2 shots, 3 shots, 4 shots, 5 shots, 6 makes, 7 makes, or maybe he makes all 8 of them. So this is discrete, right? Because I could easily list all of the outcomes that are possible. He's got 8 attempts. How many can he make? Well, he can make none all the way up to 8. Now, let's assume that he's an 85% free throw shooter. How do I find the probability of each of these events? So what's the probability of 0 makes? What's the probability of 1 make, and so forth? Well, imagine a function, right? Like in algebra, a function, you plug in x and you get something out. So you plug in the input and you get out an output. Well, imagine a function where I plug in 2 and I will get the probability of making 2 shots. That is a probability function. You plug in the outcome you're looking for and outspits the probability of that outcome. So again, that's how I could fill in this probability distribution. I could say, all right, how do I find the probability of 8? Well, let me use my function. Let me plug 8 into my function, boop, 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 and out comes the probability of getting 8 shots. Now again, we're not ready to know this function yet, but all I want you to understand right now in this intro video of random variables is just that a function does exist to calculate this for you, right? So right now, we don't know the function. I just want you to understand the existence of the function, but let's actually try to explore how we could do this by hand. All right, so when you do this by hand, we have to make sure we understand a couple things. There are 3 really important things you got to understand. First, each attempt is either a make or a miss. 85% for make, 15% for miss. There can only be 2 possible outcomes. Make, miss. There cannot be a 3rd or 4th or 5th outcome. All right, the probability of a make doesn't change from shot to shot. So if Josh has an 85, was that his name? Gosh, I forget already. Jay, his name was Jay. Sorry, I knew it was a J. So Jay has an 85% chance to make a shot, and that needs to stay consistent for every single shot. It can't go up and it can't go down. He can't get a hot streak where he has an increased chance, or he can't have a cold streak where he has a decreased chance. It's got to stay 85%. And the third thing is that each shot's outcome is independent of the next. So on his first shot, whether he makes or misses it, that does not impact the second shot, or the third, or the fourth, or the fifth, all the way down to the 8th shot. So let's actually do this, right? So again, I'm imagining a function where I plug in 5 shots made and I get out the probability. Now, I am going to teach you this function a little bit later on in this unit. But right now, I just want you to understand that we need to be able to do this by hand, right? Which is kind of like true in algebra, right? You need to know that there's shortcuts, but you have to start knowing how to do it by hand. So I want to make 5 out of 8 shots. So let's think of a scenario. So I'm going to use a circle for a make and an X for a miss. So he needs to make 5 out of 8. So let's say he makes the first, makes the second, misses, misses, makes, misses, misses. So there's his 8 shots. 1, 2, 3, 4, 5, 6, 7, 8. Whoop, I did 1 too many. I thought I accidentally counted too many there. Sorry about that. There's his 8 shots. Now think about this. He had 8 shots, and he wants to make 5. That means he has 5 makes and 3 misses. 5 makes, 3 misses is his 8 shots. Now, what's the probability of this happening? Well, every one of the makes is 0.85, and I'm going to raise that to the 5th for the 5 makes. It just saves me time rather than doing 0.85, 0.85, 0.85, 0.85, 0.5. And then every one of those misses is 0.15, which there are 3 of. So this is the probability of 5 makes, 3 misses. But guess what? I'm not done yet because there's other options. Another option could be miss, make, miss, make. So there is another option that still consists of 5 makes and 3 misses. Now the good thing, right? The good thing is that every possible scenario that has 5 makes and 3 misses will look like this. 0.85 to the 5th, 5 makes. 0.15 to the 3rd, 3 misses. But what I need to consider is how many different outcomes there are. because each of these individual outcomes is technically different, right? Another one could be maybe he gets his 5 makes all in a row and then he ends with his 3 misses. Or you know what? Another one might be he starts with his 3 misses and then he ends with his 5 makes. Or maybe another one is he misses, makes, miss. Again, my goodness, there's tons of options. I don't want to sit here and figure them all out, and that's where the function's going to come in handy. But what I need you to understand right now is the only good thing here is that every single scenario involves 5 makes and 3 misses. What I need to figure out is how many different ways this can happen. Now, again, they're all the same. So maybe I find out that there's 22 ways that can happen. Well, okay, the good thing is that they're all the same, so I can just times it by 22, but it's not 22. So we need to figure out a function that's going to help us understand how many different ways this can happen to make this problem very easy. But once I have this function, then I could just start plugging in. I could plug in 0, get the probability of making 0 shots. Plug in 4, get the probability of making 4 shots. Plug in 7, get the probability of making 7 shots. So we are going to learn that. But again, I need you to understand the idea that if he wants to make 5 shots, there's got to be 5 makes, there's got to be 3 misses. That's pretty easy. But the second thing that I need you to understand, that's for some kids a little bit tricky, is that there's lots of different possibilities. And I tried to list a couple here, but there's a lot more. If I'm correct, I'm actually have to check my own math, but I think there's like 56 different options here for making 5 and missing 3. And that's what we need to figure out how to get that number. That way we can make this a little bit easier for us, and we'll discuss that later on. But the main objective of this video is simply to have you understand that random variables are letters. They take on the possible outcomes, the possible numeric outcomes of a random process. And there are 2 types, discrete and continuous. And that once we understand what this all is about, then we can make a probability distribution. And again, a probability distribution is just some type of display that shows all the outcomes and all the probabilities. Now, if it's continuous, making that display can be very, very tricky. And that's where we're going to have to do some work on that later as well. All right, more to come on this topic of random variables for sure. See you in the next video.